Okay, so in this chapter we're going to talk about variability. So variability provides us a quantitative measure of the differences between scores in the distribution, and it describes the degree to which the scores are spread out or clustered together. So it describes the distribution of our data, and it tells us how well the individual score or group of scores represents the entire distribution. So the higher the number, the more the variability. The lower the number, the less the variability. So the range is sometimes considered kind of a crude measure of variability because you're simply taking the highest score and subtracting the lowest score. And you get this individual number, so 12 minus 3 is equal to 9. But in published reports, when I do report out scores, I will typically give the max and the min and let people kind of compute themselves the range. But when you're asked what the range is, you take the max and you subtract the minimum score and you get the range. So you've seen this before. This is a sigma squared, and the sample variance is an S squared. So the population parameter is written in the Greek letter, and the sample statistic is written in the Latin script. So variability can also be defined in terms of how close the scores in the distribution are to the middle of the distribution. So the average of sum of squared deviations around the mean is called the variance. And I'll explain that as we get closer, as we move along. So you remember this from last week. We have the deviation score, and then you take the score, the individual score, and you subtract the mean from it. And remember, when we sum them all together, we got 0. So we decided to square them so that the negatives would go away. So when you divide the sum of squared deviations by n, you get the population variance. Okay? So you divide by n, the total population, and you get the population variance, written as sigma squared. But here's a little caveat. We rarely know the population variance. We estimate it by using samples. And so we have to do, we do the exact same thing, but notice I've switched my sigma squared to an S squared. And this is the sum of the squared deviations from the mean, and I divide by n minus 1, and that makes it a sample variance. And when we do that, we divide the sample size minus 1, which is for the degrees of freedom. Now, the what? What is degrees of freedom? So in general, here's the definition that I know doesn't make any sense, but just bear with me. In general, with a sample of n scores, the first n minus 1 scores are free to vary, but the final score is restricted. As a result, the sample is said to have n minus 1 degrees of freedom, and it's written like this. This is important to know. DF stands for degrees of freedom, and that is equal to the sample size, take away 1, so n minus 1. Okay, clear as mud. So let me give you an example. We have $20 and there are 3 of us. Amy has $10, Anna has $5. How many dollars do I have? Well, if you know Amy has 10 and Anna has 5 and you know the total, I'm stuck with having to have $5 because the 10 was accounted for and the 5 was accounted for. So what was left over was my score. It was fixed. So it had to be $5. We had 2 values that could have been anything. She could have had 11, she could have had 4, she could have had 2, she could have had 8. We had 2 degrees of freedom, these two, Anna and Amy. But once they were set, then the last one is fixed. It had to be that value. So it had 2 degrees of freedom. So why do we do that? In the chapter, they talk about biased and unbiased statistics. And sample variability tends to underestimate the variability in the corresponding population. So if I take a sample and I calculate a statistic, it will underestimate the variability in that sample. to correct for this, we adjust by dividing by n minus 1. So we use this degrees of freedom so that we have an unbiased estimator. And it's beyond the scope of having to figure out why all that works. Just know that you have to use the degrees of freedom. Once we get into SPSS for calculating statistics, it's all listed. You don't have to calculate anything. So, but I want you to know what it is because you will have to use it when you report out. Okay, so standard deviation is the most commonly used and most important measure of variability. It determines whether the scores are generally near or far from the mean, if they're clustered or if they're scattered. They work just the same as the variance because this is the square root of the variance. It approximates the average distance from the mean, and the goal is to measure the standard or typical distance from the mean. And how do we do that? So here's like a little formula. If this is my score, these are my scores. Let me add them up and divide by 4 to figure out what the mean is. So if I add these up, I get 20. I see that I have 4 scores, so 20 divided by 4 is 5. And then eventually my degrees of freedom will be 4 minus 1, which is equal to 3. So sample size minus 1 is 3. File that away for later. So now we know that our mean is 5 and our individual score are listed here. So we have 2. So 2 minus 5 is negative 3. We square it. We get 9. 4 minus 5 is equal to negative 1. We square it. We get 1. 6 minus 5 is 1. We square it. We get 1. 8 minus 5 is 3. We square it. We get 9. We add these guys up, which it just happened this way. But it doesn't always end up the same as the original score. But the sum of the square deviations from the mean is 20. So to get the variance, which is the s squared, we say 20 divided by the degrees of freedom. We're doing the sample variance. We get 6.67. Take the square root of that side, take the square root of that side. We get 2.58. That is the standard deviation for this distribution of scores. The mean of 5 and a standard deviation of 2.58 or 2.6. So the steps to calculating the standard deviation, I'm going to tell you, but you don't need to do it. The computer will do it for us. You determine the mean for the scores. You determine the deviation, the distance from the mean for each score. You square the deviation score, and then you divide by the degrees of freedom, and then you take the square root of the variance. And that gives you the standard deviation. So, looking at these two distributions, it's different for each distribution. Here we have a mean of mu at 80 with a standard deviation of 8. Here we have a mean of 16 with a standard deviation of 2. Each distribution is different. And here, if I were to have a score of 19, I'm far from the mean. I'm beyond the 2 standard deviations. I'm significant, or maybe not significantly, but I'm above the mean. Whereas here, if I have an 82, I'm not that far from the mean. I'm still within 1 standard deviation. Okay, so the standard deviation and descriptive statistics. So these describe an entire distribution. Rather than listing out all of the individual scores in the distribution, research reports typically summarize the data by reporting only the mean and the standard deviation. All right, so I want to show you this. In a standard normal distribution, in the dark orange, 68% of the observations will fall within 1 standard deviation of the mean. In 2 standard deviations, plus or minus, you'll observe 95% of the scores. And when you go out to 3 standard deviations, you've captured almost 99.7. So almost all of the scores will have fallen under the curve when you go out to 3 standard deviations, plus or minus. So with that in mind, here's a sample, an example of any distribution with a mean of 36. So notice we're talking about a sample mean, a mean of 36 and a standard deviation of 4. So in this case, 1 standard deviation is denoted by 4 points. Okay, so if we go plus or minus 4, we're within 1 standard deviation, which is 68% of the observations. If we go out 2 standard deviations, so plus or minus 8, we've captured 95% of the observations. If we go out 3, we've captured 99.7% of the observations. So in very general terms, the goal of inferential statistics is to detect meaningful and significant patterns in research results. Variability plays an important role in the inferential process because the variability in the data influences how easy it is to see patterns. And if you have low variability, patterns are seen clearly, whereas high variability tends to obscure any patterns that might exist. And so why do we do that? We do this because we want to be able to use our sample statistics to estimate or generalize back to the population from which they were drawn. So if I'm looking at high school teachers of science, my population is all high school teachers of science. My sample is the high school teachers of science from district whatever ISD, and the statistic I find with those sample, we want them to generalize back to the population. And in order to do that, we use inferential statistics. Okay, so quickly, just to remind you, mu is a Greek letter, and it is the population mean. M we're going to use as it's a Latin letter, so it's for the sample, and it means mean. We also might see x bar, but not commonly. Sigma squared is variance, S squared is sample variance. Sigma is population standard deviation, S is the sample standard deviation. We'll talk about, you'll see sum of squares in the text if you're reading the text, and the only difference is this mu is here and this mean is here. Everything else is the same. Population has to do with the Greek letter, which has to do with a hypothetical, because we don't ever really know the measure of a population, because if we did, we wouldn't need statistics. So we use the mean of our sample to represent the population. And we'll do way more on this as we go forward, but this is just laying the groundwork for how inferential statistics works.